Hi, and welcome to this video about negation. In this video, we will explore what negation means, how it works, and how to work with multiple negations. Let's get started. First, let's review a bit. Negation is a part of propositional logic. Remember that the primary purpose of propositional logic is to determine whether declarative statements, arguments, are true or false. Here's a quick reminder of some of the symbols that we use. A lowercase letter represents a variable. An uppercase letter represents a predicate. An upside down A represents the universal quantifier, or for every. And a backwards E represents the existential quantifier, or there exists. And two dots on top of one another represent such that. For example, the statement, there exists an x such that x squared equals 9 is true, since 3 is an x value that makes the equation true. If x is our variable and p of x is the predicate, x squared equals 9, then our statement looks like there exists an x, p of x. On the other hand, for every x such that x squared equals 9 is clearly false because there are plenty of x values that make the equation false. Fully symbolic, the statement reads, for every x, p of x. Now, what exactly does negation mean? Negation means basically what it sounds like, to make a statement negative. Any statement can be negated. The word not is perhaps most commonly used to negate a statement, but other words and phrases can be used as well, such as no, it is false, it is not the case, and it is not true. When a statement is negated, its truth value is the opposite of what it was. Sometimes a truth table can be a helpful illustration. How negation works. Let's revisit the statement, there exists an x value such that x squared equals 9, which we've said is true. Negating it should produce a false statement, which it does. There does not exist an x value such that x squared equals 9. Note that the negation of this statement is not, there exists an x value such that x squared does not equal 9, because x squared does not equal 9 is a different predicate for a different time. We are testing x values that make x squared equals 9 true or false, not x values that make x squared does not equal 9 true or false. Likewise, the statement for every x value x squared equals 9, which we've said is false, is made true by negation. It is not true for every x value that x squared equals 9. The symbol for negation is this. Let's add it to our list. Now, back to our examples. We negated the statement there exists an x value such that x squared equals 9 by saying there does not exist an x value such that x squared equals 9. Symbolically, we originally said there exists an x, p of x, which is true. It can be negated by saying there does not exist an x, p of x, or in other words, there does not exist an x value such that x squared equals 9. Or we could say that for every x, it is not true that p of x, or for every x, x squared never equals 9. Both the negations have the same meaning and are truth equivalent, in this case both false. In our second example, we begin by saying, for every x value, x squared equals 9, which we know is false, and negated it by saying it is not true for every x value that x squared equals 9. Symbolically, we originally said that for every x, p of x, which is false. It can be negated by saying there exists an x, not p of x. Or in other words, there exists an x such that x squared is not equal to 9. Or we could say, not every x, p of x. Or in other words, not every x value makes x squared equals 9 true. Again, both negations have the same meaning and are truth equivalent. In this case, both true. Also in this case, the term counterexample comes to mind. For every x value, x squared equals 9. False. Here's a counterexample. Let x equal 2, for instance. Let's try some practice. Evaluate each statement and show its negation has the opposite value. Every voter is at least 18 years old. This is true, according to the law. The negation would be, not every voter is at least 18 years old. And this is false, because the voting age is 18. Every composite number is even. False. Some composite numbers are odd, such as 15. The negation would be, not every composite number is even. This is true. Multiple negations. Statements can be negated multiple times. Since one negation flips the truth value of a statement, a second negation flips it back. Let's expand our truth table. Therefore, saying there exists an x value such that x squared equals 9 is truth equivalent to there does not exist an x value such that x squared equals 9. Symbolically, this would look like this. Now I want you to try some on your own. Pause the video and complete the chart. All integers are rational numbers. Here's what that looks like symbolically. And the truth value of this statement is true. Not all integers are rational numbers. Here's what this looks like symbolically. And the truth value for this statement is false. It is not the case that not all integers are rational numbers. Here's the symbolic expression for this statement. The truth value is true. There exists integers that are not rational numbers. Here's what this looks like symbolically. The truth value for this statement is false. It is false that it is not the case that not all integers are rational numbers. Here's what this looks like symbolically. And the truth value for this statement is false. There do not exist integers that are rational numbers. Here's what this looks like. The truth value for this statement is false. I hope that this video increased your understanding of negation. Thanks for watching and happy studying.